Now, in any sort of science course, you're going to be taking measurements, and we always want to evaluate our measurements to determine a couple of different things whenever we're looking at those numbers. And the two, I would say, most important measurements is precision and accuracy. Precision is going to be looking at how close a set of measured values are to one another, and basically the fineness of markings on a measurement tool. Accuracy, on the other hand, is how close a measured value is to that true value. And it's going to tell you a little bit about the calibration of a measuring tool. So we see these different options, A, B, C, to display dartboards or use these two dartboards to compare precision and accuracy. So if we look at this first one, this A right here, this is going to show that this person was very precise. They hit one spot on the dartboard and they hit that spot over and over and over again. Now, if you look at, in contrast, C, this person threw the darts and they were all over the place. You know, they were obviously aiming for the bullseye. I don't really know how to play darts. I always assume you always throw for the bullseye, but I think that there's some sort of counting involved. At any rate, this person will imagine that they are throwing towards that bullseye every single time, and they hit, maybe the center one hit, but all these other are all over the place. So they weren't very consistent in where they threw their darts. So they were not precise. Also, if they were aiming for that bullseye, they were not accurate. So if we look at answer option B, on the other hand, this person was both precise and accurate. They were accurate because they hit the bullseye every single time. And they were precise because, well, they hit in the exact same place every single time. So your aim and your goal is really to be both precise and accurate whenever you're taking any sort of measurement. So whenever you're doing any sort of measurement, this shows, for instance, a ruler. How can you make this measurement, or how accurate can you be with this measurement? And so if you look at the two sides of this ruler, we've got, well, I guess this would be a meter stick. You've got centimeters on both sides. So we've got 1 centimeter, 2 centimeters, 3, 4, 5. Okay. Now, if you are looking at this side, the top side, you can clearly see that there's 4.1, 0.2, 0.3, 0.4, and 0.5, 0.6, 0.7, 0.8, 0.9, and 5. Okay, so it's kind of difficult to see, but this line right here falls right before 4.1, so slightly before 4.1. Okay, so it's reasonable to say that this is less than 4.1, and therefore you can make a pretty reasonable approximation as to what that would be. And you safely be able to say, or I think that you can comfortably say that this would be something like 4.09, because you know that this measurement right here is not equal to 4.1. It's less than 4.1, in fact, but, well, you have to make some sort of prediction about that. So this side would be, well, precise up to 2 decimal places. On the other side of this ruler, or on the other side of this meter stick, well, you can say that the measurement is between 4 and 5, so you'd be able to say it's, well, 4.1. Because you don't have these hash marks there. You can't make a reasonable estimation as to what that measurement is. So whenever you're looking at a tool to measure something, you always want to look at what are the hash marks on there so that you can say something about the accuracy of it and the precision of it. Okay, now to explore those a little bit, you have significant figures. You always want to report every digit that you measure with certainty, plus the first digit for which you must estimate, which is what we saw. We saw 4.1, but we knew that we were less than 4.1, so we said 4.09. Okay, just like if that number was slightly above 4.1, we would be able to say 4.11, for example. Okay, significant figures are limited by the tools used to make measurements and will determine how we round our calculations. So if that number had, or if that line had fallen directly on that 4.1, we could comfortably say 4.10. Okay. So when you're counting significant figures and you're looking at numbers and evaluating them, you can work with a couple of rules. So reasonably counted and defined numbers have an infinite number of significant figures and will not limit your calculations. So there are 92 people in a room. If we were in a lecture hall, there'd be something like 105 people in that room. 1 kilogram is 1,000 grams. Okay. Now, when you're looking at numbers, though, you want to be able to define them as significant or non-significant. So the first rule that you can follow is all non-zero digits are significant. So 42.7 has 3 significant figures. There are 3 numbers that are non-zero digits. Okay, all sandwich zeros, so zeros that are between significant figures, are significant as well. So 2.03, there's nothing you can do to omit that 0 and have it be the same thing. So that 0 has to be considered a significant figure. So this 2.03 has 3 significant figures. Let me go ahead and erase that X there. There we go. Zeros at the beginning of a number are not significant. So here we have 3 zeros and none of them are significant. There are only 2 significant numbers here, and they are 3 and 3. Zeros at the end of a number are only significant if the decimal place, or if the decimal point is written. So 3.30 has 3 significant figures compared to the number 3,000. So 3,000, that's a kind of ambiguous number compared to 3000.0. Well, this number has 1 sig fig, and this number has, let's see, that would be 5 sig figs. 5 significant figures. Now, let's just go ahead and count these, and so if you want to go ahead and come up with a number beforehand, go ahead and pause. Count the number of significant figures. There is 1, 1, 6, and then this one right here is 3. So the reason is no decimal. The decimal is to left. And this one, well, this has a couple, oh, oopsies. All zeros to the right of decimal. And then this, our decimal is to the left. And we have a sandwich 0. Okay, so that's what's going on that slide. Now, how many significant figures are in this number? Okay, so 8675309. We've got, well, we have 1, 2, 3, 4, 5, 6 numbers that are non-zero digits, and this 0 is between. It's a sandwich 0. So we've got a total of 7 sig figs. How many significant figures are in this number? Well, let's see. That's not significant. This is, this is, this is, this is, this is, this is, this is. So that's 2, 4, 6, 7. We've got 7 significant figures in this slide, or on this number right there. Now the last number that we're going to look at is actually rounding. So rounding a number like 29.95 to 3 sig figs. Now let's consider some of our options. So A, that has 3 sig figs. B does not have 3 sig figs. C does not have 3 sig figs. D does not have 3 sig figs. So we're left with A and E. Okay, so A and E are the only 2 numbers that have 3 significant figures. Now if you look at A, is there any rounding there? No, you just dropped off that 5. But this was rounded. Our answer would have to be E, because if it's 5 or above, we round up, just like a grade. 89.5 rounds up to a 90 in my books. Okay, well I hope this is helpful, and have a good one.